So in this section I am going to teach about states, state graph and transition states. So what is the meaning of state, what is the meaning of state, why we are defining the state graph, and what are the connections to define the transition testing. Fine. So first we have to know about the introduction. First, these state graphs are nothing but the finite state machines. Okay, first we have to remember that when we are entering into the concepts of state graphs, it is connected to the finite state machines. Okay, so the finite state machines is connected with the software engineering to build the Boolean algebras to the logic. Okay, to build the Boolean algebras for the logic is the first point we have to understand. Second one, in this strategy, okay, when we are building this concept or when we are building the particular graphical representation, we have a strategy to define the state machines. How we are defining the state machines are nothing but by the software structure. How we are defining means by the three types, which is nothing but first one, software structure. Okay, second one, software behavior, and the specification of the software behavior. These are the three important strategies which are used while developing or when we are building the software. Next, these finite state machines, how these finite state machines are implementing means to design for the options. Okay, to design the options it is using. First, we have to know about the introduction. What is the state graph? State graph is connected with the finite state machines, right? So in this first step we will define about the finite state machines, how it is connected. Finite state machines is the fundamentals of the software engineering which is used for Boolean algebra. Okay, which is used for Boolean algebra for logics. Second one, these strategies of testing is connected for the software which to build the particular need for the software structure or a software behavior or the specification of the behavior. Next, these finite state machines also implemented. How it is implementing means by the software which is taken by the design options. To design the options we have to take the software for the fundamentals. Okay. Next one, what is the state graph? We have to define the state graph. Okay. So how we are defining the state graph means, see carefully, the state is the definition. How we are defining means the combination. Okay, the combination of the attributes. Okay, the combination of the attributes. Class is different from attributes. Like class is the main heading and the attributes are what are the child process or child things, right? So it is the combination of the attributes which is belong to the time. For at that period of time it may be a person or a thing. Okay, so the state graph is nothing but how we are saying the state graph is defining about the combination of the attributes. Okay, combination, how it is connecting means combination of the attributes which is a person or maybe a thing. Okay, next one, we will take a small example. What is the small example? Automobile engine. How we are taking means automobile engine we are taking. So in this while we are driving, we will know about first gear, second gear, third gear, fourth gear. Okay, neutral gear. See this, neutral gear. Okay, reverse gear. These all are the examples of attributes which are connected to build the state graph. Okay. So the state graph is nothing but the combination of the attributes is we belong to the time at the period of person or a thing. So we took an example, a small example is the automobile engine which is used to transmit the transmitter. So in this we have a small attributes examples which is nothing but first gear, second gear, third gear, fourth gear, neutral. So this is the view. Next, So next we also defining the small example which is detecting the sequence. In sequence order, how we are detecting the particular variable. Suppose we took as ZC, okay, ZC, ZC. How we are defining this ZC, ZC in each and every stage while we defining the state graph. First we have to assign, okay, first we have to assign, okay, first we have to assign about Z is detected or not, okay. First we have to assign Z is detected or not, okay. Okay, first Z is detected or not. So next ZC is detected or not. Next ZCZ is detected or not. ZCZ is connected. So we have to form ZC, right? So ZC we have to connect. So first we have to know Z is connected or detected. Next ZC is detected. Next ZCZ is detected. Next ZCZ. So it is a sequentially detecting one by one, right, to form the sequential character which is number identified by the particular keyword, okay, particular keyword, right. So these what we took the variables of ZC, we are defining in the state graph. So we have to define the state graph. So first how we are defining means, first we have to assign the null variable. First we have to assign the null variable. So this null variable is nothing but a null variable, okay. Next we have connected as Z. Next we are connected as ZC. Next ZCZ. Next ZCZ. So in these statements here, Z is connected to ZC, ZC is connected to ZCZ, ZCZ is connected to ZCZ. So in these variables we have to assign the particular, in these nodes we have to assign the variable. So the first variable is A is connected to the none state. Next ZC have two nodes variables like AC. Next we have to connect one variable, that is nothing but A. But last we have AC. So the self loop will be indicated as ZC. Okay. Next, overall calculation of ZC is A. These all statements we will calculate here as a self loop which is any state. So what we have to see means the first state and the last state will be indicating the self loops, and middle of the states will be indicating the parallel links, okay. So middle of this nodes will be indicating the parallel links, and the last node and last node indicating the self loops which are indicating as ZC, ZEA, because ZEA is a starting node, none is an ending node. So each and every node is connected with the end node, okay. So this is the state graph how we are assigning the particular nodes of a variable, okay. Next, so next we have to know about inputs and transitions. How we are defining the inputs and transitions means whatever we are subjected, whatever we are giving as an input, so it will be changed, okay. Sometimes it may be changed or sometimes it may be a change. If we have by transferring the change, when we are giving a chance to change, it is called as a transition made. So it is the transitions which gives the join to state, okay. Next one, the inputs. What are the inputs of transition means what are the links which are waiting, means which is given to the axis of first link and second link. Next, this is the one link, each and every link has to connect it each every input, okay. Each and every node, okay, each and every node must be connected with the input. So if Z is a node, right? If Z is a node, ZC as a node, each and everything is linked to each other for independent unit. Okay, next one, each unit of transition as a subsequential. Why we are having the subsequential means, see, another node is adding, so it is also have a subsequential. Why it is adding subsequential means it is having the parallel links to transmit the data. Okay, to transmit the data we are giving the input. Next one, we will define about the single thing, which is nothing but we have to know clear view about finite state machine. So we will, how we are defining finite state machine means, we will define this device as a finite number of transition states and finite number of states will be combined to combine between the states. Okay, finite state machines is nothing but, see, the finite number of states and the finite number of transitions. Finite number of transitions between the states is nothing but a finite state machine. Okay, what is the definition of finite state machines means? It is the abstract which is giving the state graph to form finite number of states and finite number of transitions, finite number of states and finite number of transitions between the states. Between the states are nothing but finite state machines. Next, in this, after overall connectivity of transitions and states, how we are getting the input. So the output is always be linked to associate. Okay, to link to associate. So in this outputs also, first we have to know whether it is labeled or unlabeled. So the labeled data or unlabeled data will be recognized by letters or words. So in this method we will define about letters and words to separate the inputs. How it is separating? First thing is nothing but input / output. Next one, the output what we are observing. Okay, second part, the output what we are observing, it will be explicit output. Sometimes the output may exist or may not be exist. So in that point also it will be explicit to for the devices to somewhat it is difficult to identify. Next one, the output of the links are weighted. Why it is weighted means A to B. Okay, it is weighted because I is equals to 10. So it is a weighted statement. Okay, so when we are giving the input, it is weighted statement. Then in the transmission of the with the same output. Okay, when we are taking the input, the same output of transition also same. Then it will be equal to input 1, input 2, input 3, so on by output. Okay, if it is input independent, then it is a input dash / output. If it is independent variables having the same output, then it will be a input 1, input 2, input 3, so on, input so on by output n. So this is the calculation when we are doing the finite state machines of any inputs. Okay, next we will define about the state table. Okay, how we are defining the state table means, okay, next we will know about state table. Means the state table, how it is connected means by the finite machines to form a Boolean algebra to the logic, right? So in this state table also, when we having the big state tables or big state form graphs, okay, it is very hard and complex and very clustering method to identify the particular need. Okay, see, first thing, big state graphs are clustered and very hard to follow. Okay, it is clustered and very hard to follow. Next one, the representation of the state graph. In this representation of the state graph, always be connected with input, output and transmissions. They are the three needs to satisfied while developing the state graphs. What is not nothing but first input, output and transitions. See, it's specifying the states of inputs, outputs and transitions to identify the convention of the states. Next, the following conventions, how it is convecting the states means, first we have to know about rows and columns. Okay, in KV charts we will in 3 variables we are defining the rows and columns, right? So here also the state tables also, how the convention of the states will be defining is made by specifying inputs, outputs and transmissions, right? So these are converted into following steps, which are nothing but first one row, next one column. Okay, first one row, next one column. So each column is corresponded to the state. First row is nothing but state, column is nothing but input conditions. Okay, so each row is connected to form a single stage. In each column is corresponding for the input what we are giving. So what is the state is defining the row, what is the input conditions, what are the input means internally, what are the input variables what we are giving means the columns will be identified. So this is the small example how we will identify the state table by defining the graph. So this is the last thing which we will define clearly about the state graphs, okay, of a transitions. So we have to know about how it is the state graph is defining and how we are defining the state table. So in state graph, okay, there are the 4 variables which is nothing but 1, 2, 3, 4. So 1 is connected to 2. Next, 1 is connected to 4, right? 2 and 4. See, x and x dash variables we are defining 2 and 4. Next, we will see about 2. 2 is connected to 1. 2 is connected with 3. 1 and 3. Next, we will define about third one. 3 is connected with 2. 3 is connected with 4. 2 and 4. Next, we will define about fourth one. 4 is connected to the 1. 4 is connected with 3. Okay, 1 and 3. See, the next state variables of x and x dash we already note down. Next, we will define of z nodes. Z nodes we already know about the single variables. In single variables what we define 0, 0, 0, 1, 1, 1, 1, 0. So these are all the statements which are defining. Okay, we can add anything. We can add a 5, okay, 6, 7, 8. Okay, I will give you another example. I will give you another example. Okay, 5, 7, 10, 15. Okay, 5, 7, 10 and 15. Okay. Okay. So I have drawn a new table. Okay. So we will see first one. So first state. This is a states. This is x and x nodes and this is z nodes. So z nodes are common 0, 0, 0, 1, 1, 0, 1, 1. Right? Here we will define about fifth node, next 7th node, next 10th node, next 15th node we will define 5th state, 7th state, 10th state and 15th state. So 5th state is connected with 7 and 10. Next 7th node is 7th state is connected with 15 and 5. Then next 10th state. 10th state how it is connected means 5 to 15. Next 15th state is connected with say 7 and 10. So this we have to explain how we are defining the state graphs when we are converting into the table. Okay, the state graphs, what is this? First we will know about what is a state graph, what is the finite state machines, and what are the independent variables how we are using. Okay. So in state graph means we will define the states of strategies by the inputs and outputs and transmissions. These strategies also converted into two variables, two things which are nothing but row convention and column convention. In row convention we will define only states. but in column convention we will define about input conditions. Okay, in finite state machines are nothing but the fundamental functions of the software which is converting the Boolean algebra to the logic. It is forming from the Boolean algebra to logic. Okay, so in these statements we are defining a small example to identify the states. So ZC I have, it is must be identified by sequential order. So one by one we have to enter. So Z, ZC, Z. So ZC. So these are the four things I have drawn. So how it is represented in state graph means last two nodes will be always be self nodes. In middle of the statements will be a parallel node, right? So the first node always be a null statement or end statement. This is end point. Okay. Last node means starting node. Starting node, end node. In middle of the things is Z, Z. Okay, these are the nodes. So starting first node we have to know about ZC. So how we are connecting the variables we have to know by describing the state graph through the state transitions of a table. Okay, to create the table only it is your explanation how we are defining or how we declaring through an example of an expression of ZC. Okay, thank you.